to find exact solutions for. So once you've got solutions, it's useful to use those to produce new solutions. T-duality is one of the ways you can do this. And there are, I'm going to underline this 3 times, many generalizations. So let's say we have U1 to the n. So instead of just having one U1 isometry, you can have multiple U1 isometries. This corresponds to, rather than, so Fritzo was asking earlier, you should be thinking of this as a circle bundle. This would correspond to a torus bundle. Then you can have a billion, me, symmetric, and the list goes on. TST and U2.
TST is also.
Yeah, so TST is it's another solution generating technique. The idea is that you take a type 2 additive solution, you do a T-value transformation, and then you kind of do a transformation in the dual space. So you shift by some coordinate with which you also have an isometry, and then you T-dualize back. So it's like a way to deform your original space.
Don't forget the higher one.
Yeah, and U-duality is very good, very good. Okay, so maybe this is, oh no, you took my card. For a review of these ones, see my lists. Probably the resource I would recommend most if you want to learn about any of these. If you want to learn about these, you can probably ask me and I can find some good references. But the point is that this is the simplest possible example of T-duality, and there are many different avenues that you can generalize this. Okay. So I just want to say that the Busher rules are local. Busher rules are local. What about global stuff? And when I say local, I mean the Busher rules are kind of inherently written in some coordinate patch of your manifold, right? I've got a coordinate description of a metric, I decompose that in a way that's valid within this coordinate patch, and then make T-value transformations give me a new metric and a new B field in some set of coordinates. I want to understand what's the topology of n hat, right? A priori it's just some manifold with a metric and a B field, but what is its structure? Okay, very good. So in order to discuss that, so this now is moving on to the work of Peter Buckner, a PhD supervisor, and his collaborators. And the setup here is precisely what Fritzo was talking about earlier, where whenever you want isometry, we want to think of this as a circle bundle. So the setup is that you literally start with a circle bundle. So I have some fiber bundle whose fibers are circles, but more than that, it's a principal U1 bundle. Okay, so this is the thing we're starting with. So for those who maybe it's worth mentioning what this is. So what is it? It's like this. So it's a fiber bundle with a base B, total space n, and the fibers are circles. In addition to that, there is a U1 action on n, preserving the fibers, and acting freely and transitively on them.
sensitively, on values.
Yeah, on that. Yeah,
I
freely and transitively.
I understood M instead of Z, so I triggered.
Right, very strong, he's strong. No, I checked this. Very good. I'm sure I'll be wrong later, but please keep paying attention. Okay, so what is a free group action? It just means that there's no fixed points. So a U1 action, so by the way, we'll also interchangeably use U1 and S1. Which means they're exactly the same. I will use U1 when I kind of am thinking of it as a group, and S1 when it's a manifold, but often I will just completely use one or the other for random. Okay, so free action means there's no fixed points, and transitively means, well, if I've got 1 point, I can get to any other point on the fiber by applying a suitable group element. For each x, y, and fiber, there exists a G such that y equals Gx. That's the
first has utility, so unique.
Yeah, exactly. Yes, exactly. And what this means is that the orbits of G are precisely the fibers of this fiber. Fibers. And the orbit space is the base space. Orbit space. What's the orbit space? It's M pushing out by the reaction of G. This is precisely this. And I'll often write it as this.
You have
I do it from the left. I can do it from this side if you like, but then it makes all my other pictures gross.
You like the left one?
Yeah, it's a left action.
Well, this is not a acting, that's the inclusion side.
No, this is an action.
Yeah, but it's also written like
This is true.
At the same
How does
time,
what they mean?
It's both, right? It's involved, right?
yeah, this
No, but you also say that if you have a fiber bond when there is no action, and you also say F and then you write this.
Yeah, but here it's both.
Sorry?
It's both.
Maybe we can talk about
This is both the fiber and the group action.
I understand, but okay.
You can, yeah, get rid of this stuff. But anyway, yeah, I write S1 here when I mean both. I mean S1 and A1.
No, I'm fine, I'm just complaining about the common notation of what you're
Very good, very good. Okay, so this is the setup that we're in. I'll now move to a different world. Are there any questions so far?
So these Langlands duality will be also topological? So these Langlands duality you are going to be topological as well?
Yeah. So it'll be to do with the structure of M. Here M is our total space. So now take M to be a group. This is the smallest of the.
No, it's like before the topological, now you're going to talk about topological aspects of it.
That's right, yeah, that's right. So in order to talk about the Langlands duality, I need to mention the topology. And I will try to keep this brief because I do want to talk about the Langlands dual at some point. Okay, but so this is the general setup, and okay, and it is a fact, a theorem, probably several theorems, which give us a classification of principal U1 bundles, principal S1 bundles. In particular, they're classified after isomorphism by elements of some cohomology. Principal U1 bundles. Elements of, what is it? It's the second cohomology of the base. That is another way of writing this. Principal U1 bundles over some base B are in one-to-one correspondence or in bijection with elements of this cohomology group. Very good. So what this this is saying is that if I have a given principal circle bundle, which is what I'm starting with, then it's classified by an element of a cohomology, it's described by a cohomology class on the base. Up to isomorphism at least. And this isomorphism is realized explicitly by the Chern class or the Euler class of the bundle. So if you're used to thinking about these things, that's something you can think about. And in addition to this, so we have a circle bundle, which is classified by some cohomology class of the base. We also assume there is okay, I have a few adjectives I need to write. What is it? Closed, invariant, integral, freeform. On the total space A. So for those who are wondering how this is relating to what Busher was saying, this circle bundle thing is related to the fact that we have a U1 isometry. It partitions our manifold into a fiber bundle, whose fibers are circles. The group action here is the flow of this U1 isometry, and this three form that I write down here, I'll say huge.
It wouldn't be an element of HT.
This?
Enough?
This one?
Yeah.
Yes, absolutely. So, well, okay. I want to assume that okay. From the Busher thing, I would get something like this.
Yes.
Right. From the physics, the B field over here, it's some invariant B field. The curvature of this B field is going to be closed invariant freeform, and integral condition is related to the fact that I want some path integral to be well defined, and I don't really want to get into that. But the point is that this closed invariant integral freeform determines a cohomology class in H3.
I think somehow it's important that it's integral, right? Because when you do this construction, you will get curvature from this H, which is integral.
But it's an important quantum mechanically, right? Like if you're doing some classical stuff, I don't think this needs to be integral. You can, classically it's fine, but okay, so what this means is that we have two, so our topological data that we started with is essentially a circle bundle with a flux, or equivalently, it's two cohomology classes. My flux cohomology class, and this is the cohomology class representing the isomorphism class of the bundle. I'll label it as F. This is the first Chern class of the associated bundle, or the Euler class of the bundle. But yeah, this is the important stuff that we're looking at. And notice that the cohomology classes are in different spaces. This is the cohomology, the third cohomology on the total space, and this is the second cohomology on the base. Good. Okay. And now, T-duality in this context. What does T-duality says in this say in this context? It says, given such data, there is another S1 bundle. And here I will write it like this. Okay, so given such data, then there's another S1 bundle over the same base. Here, the only thing that's the same around these is the base. And it's going to have with some flux as well, and I'll call it H hat. So from this, I'm going to neutral. This determines two cosmology classes. I've got a H hat and an F hat. Then this is H2 of base, and this is H3. So there's another S1 bundle determining these cosmology classes, satisfying this set of equations. And so this is, if you like, the topological content of the Bushel rules. Okay, you've got some mixing of, in the Bushel rules, you had a mixing of geometry and
What exactly you mean by pi star? Because
oh, this is the push forward, right, yes.
But they are different degrees.
That's a fiber integration, right?
Yes.
This is the push forward, but it's integrating.
Yeah, exactly.
Okay, sure.
Or in terms of this Keystone sequence, it's the map which is
Yeah, okay.
in the kernel of what you
So you simply integrate along this circle.
yeah. So exactly. So you should be thinking of these as differential forms. And yeah, exactly. If they're differential forms, H is a 3 form, I integrate that 3 form over the circle, I get a 2 form on the base, and that's the 2 form characterizing the isomorphism class of Langlands. That's exactly that. And vice versa. So it's a duality in this sense. Okay. And I would be remiss if I didn't mention the correspondence space at some stage, which says that, so the picture here would be something like this. I have my circle bundle here, my original one, pi, and then I have my dual circle bundle over the same space, hat. I can form the double pullback, which is the pullback of this bundle via this map, or the pullback of this bundle via this map. Either way, the same thing. And this. And I don't know some of these as I have and there are some additional conditions that we require, which I won't really go into. Okay, and one thing that I would like to say also is that many objects of interest in the context of T-duality can be phrased as some kind of Fourier transform in the following sense. In the sense of you take something in M, some geometric quantity of interest in M, you pull it back to the corresponding space, you twist it by something, and then you push it forward down into visual space. And I'll give you an explicit example of this. The Ramon fields. So this is kind of maybe an aside example. The Ramon fields of let's say type 2A of string theory. So the way you get the transformation rules, or one of the ways you get the transformation rules for the Ramon fields under T-duality is you package all of these forms into a polyform. By that I mean this. So let's say I have my Ramon fields of the even degree forms. So this is a 0 form, this is a 2 form, this is a 4 form. So I added all these up and I just get a sum of differential forms. I work with some other sum of differential forms, and that gives me just a linear combination of differential forms. Then I can, so these are differential forms on my original space on M. I can pull them back into differential forms on the correspondence space, twist them. So what I do is I'll pull G back to the correspondence space. I'll twist it by this question here, which means wedging it with this other sum of differential forms. This really is the pullback.
So you're saying the exponential is
I would say that in a second. So what it is, I take my polyform, I pull it back up into the correspondence space, I wedge it with something else, and then I integrate it over the fiber, and this gives me the dual rho1 field. So of course this is going to be another sum of differential forms, and I can decompose those into different rho1 fields of type 2. This F is it's the curvature of a connection on it's the curvature of the Poincare line bundle. So curvature of Poincare line bundle on S1 times S1. And so this exponential is just the trait character of the Poincare line bundle.
What is the difference between S1 and S1 hat?
So,
S1 hat?
yeah.
Just to distinguish this.
Yes, okay. Strictly speaking, this is true for product bundles, where M is a product of something, B times S1. So here I just mean the S1 associated to this.
Okay, so is this how we prove the equivalence of K theories?
Yeah, this is like the first step in doing this. So strictly speaking, what I'm saying here is true only for product bundles, but then you do some other stuff to do that. That's one of the ways to do it. There are probably others. Okay, everyone happy so far? Because that's the review of T-duality, which took up most of my time. And now we'll do the Langlands part of it. Okay, great. Okay, so the question that these people asked in their paper was the following. Is the relationship between a group and a Langlands dual a form of T-duality? Oh, I should also mention, by the way, this stuff over here that I've talked about is for principal S1 bundles, right? So for circle bundles. There's a natural extension to torus bundles, and the basic idea is the same. It's a little bit more complicated. Now your cohomology classes are starting to be a bit wonkier. There are some restrictions on what type of H fluxes you're allowed to have in order to make this make sense. But in general, it works pretty much exactly the same. Okay, good. So this is the question. Is Langlands duality between a group and its dual group, can I think of this as T-duality in this sense of the word? And the spoiler is yes. For ATE groups.
What are ADE?
We will get there. But basically, Lie algebras have a complex finite dimensional semi-simple Lie algebras have a classification. There are three families, A, B, C, D, A, B, C, D.
Okay.
Which are infinite families, and then there are some exceptional ones. And this is saying, and so then the same is true, modulo some classifications that I might mention, that this gives you some sort of classification for groups as well, for Lie groups. And it's saying that the B and the C ones, so the groups that have factors that are of type B and C, don't work, but the other ones do. That's what this is. That's what we're getting at. Okay.
These are the Lincoln diagrams that are.
Yeah, Lincoln diagrams.
But those that have only single.
Yes.
Yeah, exactly. So
So
the
they
B,
have some name, right? Simply.
yeah. So the B and the C ones are the ones that have arrows in them. That's
Double line.
exactly, yeah. And we'll see that okay, so let me briefly recall what a Langlands group is, or a Langlands rule. Okay, in order to do that, I have to briefly mention some words that I don't like, but I'll do that. Let G be a complex, reductive algebraic group. And I don't like any of these words, or I like group. The point is that these are in one-to-one correspondence with compact connected Lie groups. Real compact connected Lie groups, exactly, yes. And those are the things that I do. So, whilst yes, I'm saying this, what I'm really thinking about is compact connected Lie groups, real Lie groups. Okay, choosing a maximum torus inside G allows us to define, okay, I'm going to be a bit, to define roots and co-roots, or root datum as it's called, co-roots. I don't want to get into a lot of details here, but essentially you have some co-roots which live in a space here, which is home of and you have your roots which live in spaces. So this is your character lattice and this is your co-character lattice. And the point is that the root datum of a group and its maximum torus defines the group up to isomorphism. So it's enough to give you this stuff, and that kind of uniquely specifies your group. Just swap these around.
So that is lambda.
Lambda cut. Yeah. I'm not sure why this is the notation, but it is.
Sorry. So this is the core and root level.
That's right. Sorry, the character. So this is it's the opposite to what I would expect. So this is the character lattice, and this is the co-character lattice. Again, these are not words that I like or use very often, but I'm sure people in the audience like and use these words. So.
And the group and the thing that determines the group is the quadruple of the
It's
CR1.
the I'll write it like this. TG, TG, which is given by these subsets C here and R here. This is the thing that determines the group up to isomorphism. This going on. The root datum. Okay, well, with the root datum, there's a kind of natural symmetry that, if you're doing this, it just kind of seems obvious that you could interchange the roles of the roots and the co-roots. Okay? So if I define the same thing, but interchanging roots and co-roots gives new it gives new data, which is just the roots first. Question? No?
But if you have it just as a set, then it's just set.
Well, it's not a set, it's an order.
Yeah, it's an order. I mean, here it has some curves and it has some roots. And then I'm saying, okay, well now look at the root data where instead of having co-roots, I use the roots. And instead of having the roots, I use the co-roots.
So just you like to use an X number in the Langlands?
Yeah, probably, yes.
Let's call it the same.
Is that better?
Yeah.
So this is the definition of what the Langlands dual is. It's the group defined by the root datum where you swap the roots and the co-roots.
Can you give us a little table? Examples.
Well, it's lost. I just said examples would be section 3. Okay. And so it's denoted by.
But so we basically say that now the roots are the elements of the duals, or not the duals, from the homomorphisms from C star to D, or not?
And I'm saying that.
Are we saying also that they are from different spaces, or we are just changing?
I'm saying that abstractly, this is just a subset of a vector space.
Yes.
And this is a subset of another vector space.
Yeah.
And I'm saying use this subset as.
As that subset of the space.
And then they define the right hand side.
Exactly.
So basically, we are taking R not from lambda per, but from lambda. Now.
Okay. Yes.
Lambda hat.
Yes. Yeah. I'm like I would maybe change the labels of these if you like.
Okay.
I can do that, but I can't be both.
So I think so. Here we should see them as lattices, right? The sublattice.
Yes.
Exactly. So abstractly, I can forget about all vector space lives in. Just
Very good. Okay. So this is denoted by this G. What is this? A check or a V? That's a check. You say check? I was worried if that was politically incorrect. And this is what's called the Langlands dual. Okay, so I've got some comments here about maximal tori being canonically isomorphic, but I think I'll skip that because I have maybe 10 minutes because we started a bit late. Okay, and I'm going to keep going. So the translation action of G. No, sorry. Right. Okay, so what do we have? We have a group and we have a maximal torus inside this group. Right? And here, rather than thinking about complex reductive algebraic groups, I want to think of compact, connected, real groups. Yep. So here, a maximal torus is really just like a copy of a literal torus inside the group. So the action of this torus inside the group, so the torus acts on the group itself. This action actually makes G into a principal torus bundle. So in the sense that I had earlier, the action of T on G makes G into a principal torus bundle. So that means I've got my total space is G, my base space is the quotient of G by its maximal torus, and the fibers are going to be something like this. And now you can ask, okay, well, this is the setup that we're going to be talking about, saying, okay, look, great, we've got a principal torus bundle. It's not a principal S1 bundle most of the time, but this is a torus bundle. I can ask whether I can ask the same question over here with the Langlands dual. And I can ask whether these two spaces are T-dual. Any questions?
So you said yes.
Good. Well, the answer is yes, but first there's some data, I feel like this is missing a few things. For instance, T-duality before was a relationship between two bundles, two circle bundles and torus bundles, but they were over the same space, right? And here you can see immediately that it's not immediately obvious that these are going to be the same space, right? A priori they could be completely different spaces.
Okay, sorry.
Spoilers! Okay, so two problems. The first problem is perhaps G mod T is not going to be the same as this guy. That could be a potential issue. The second potential issue is, well, I guess. What are we missing, right? T-duality, we had a circle bundle, but we had other data, right? We had this flux. There's no flux here floating around, right? So what's the thing? Another way to phrase this is, okay, even if the base spaces were the same, there's no like flux floating around. So if the bases were the same, you could instead ask a different question, which is there a H flux such that these are T-dual? That's another H. So
That's free flow.
yes, so I didn't guess that. Very good. The answer is yes, there is a natural three form on G called the Cartan three form, and it turns out to be exactly the right thing to use. So no flux. And actually, I'm running out of space. I'm running out of time, so I will just. Yeah, I will skip a lot of the things I was talking about. So, okay, I'll give you short answers, and then we'll just go from there. So, short answer, it is. We have that G mod T is actually the same as G check mod T check. As long as G has no simple factors of type BSC. So the lemma that I've written down that I was going to go through the proof of, but it's fine, just says that if G is a compact Lie group containing no simple factors of type BSC, then its Langlands joule is the same. So it's a compact Lie group with no simple factors of BSC, and we have this homeomorphism.
But so the trick is that for Bn or Cn, we don't have that Langlands law is the same.
Yes.
But we are basically.
No, but the Langlands joule is not going to be the same even if they don't have types A, B, and C. The thing that we have here is okay. So take your root G. Then morally, we should be thinking about this as something algebra, and it has a bunch of simple factors, right? And these simple factors are going to have various types. So maybe it has a G1, which is a type AN, or something like this. G2, which is a type DN, or something like this. Very simple. The point is that each of these classifications has an associated Cartan matrix, which is like how you classify these finite complex semi-simple Lie algebras, finite dimensional. And the Langlands duality, how it acts on these Cartan matrices is that it transposes them. Right? Because the Cartan matrix is consisting of elements which are, you've got some root, and you evaluate it on a co-root, right? Where alpha and beta range over the list of simple roots. So you get some matrix with integer entries, and swapping the role of roots and co-roots just transposes this matrix. And the thing is that A, D, and E groups have symmetric matrices. Have symmetric Cartan matrices, this is just a fact. B and C do not. And so every time I take the Langlands joule, what this means is that A goes to A. D goes to D. B and C, I think, swap from memory. I'll get there in a second. So D swap. And we have E, F, G. So we have some E. There's three of these, one of this and one of this. This, I think, stays the same. You can check that. F4, all that it does is that it interchanges the order of your simple roots, but it still sends you to F4. and the same thing with G2. So what this is saying is that under Langlands, like if I look at the Langlands tool, as long as you don't have any factors of type B and C, the isomorphism, the isomorphism class of the Lie algebra is invariant.
But then why do you consider it only for A, B, and E? Why?
I also, yeah, but there's only five of these. So A, D, E, and these guys as well.
Okay. So they are also in.
Sure.
Okay, okay.
But that's fine anyway. That's all.
What if you would have B and C and have them both?
Yeah, this is not covered in the paper. I did think about this. And yeah, it's not covered in the paper. I would have to think about it, but it's an interesting question. Yes.
So, what happens to the torus? Is it also the same, or is it?
So,
Is the
yeah, and that's that's the harder part of the proof that I was also going to skip anyway because it's hard. The answer is yeah. So you go through this and you find out that both G and G check have the same Lie algebra. Of course, that doesn't tell you that G and G tilde are isomorphic or anything. It just tells you, I guess, that their universal couplers are isomorphic. And then there's some Lie theory that you can do that says if you group them by the maximum torus, then they are actually isomorphic. Something Burrow subalgebras. I can link you. Yeah, I mean, read the paper, and I would say it's the best source of this. Okay. In the last minute, I will say that the flux they use is precisely as Ruth was guessing earlier. It's given by the Cartan freeform. So here, it's essentially I take the killing form of x with y, z. So here, x, y, and z are all elements of my Lie algebra, which I'm going to identify with the space of left invariant differential forms. Left invariant vector fields. And then these form the basis for my vector fields. So this is a thing which takes in vector fields and gives me out some number. So it's a differential form, a differential 3 form, and there's some normalization factor here. And with this normalization factor, it's integral, closed, and invariant. And turns out to be precisely the thing which implements T-duality and is and so the final theorem says precisely let G be such a group with H given by this. Then and this is the diagram that you have, and so G and G check are related by T-duality. And because I can't give a talk without giving an example, it's illegal. I'll do one small example, which is SU2, G equals SU2. Of course, I'm going to do more interesting things, but this will do. The maximal torus of SU2 is just a copy of U1. Okay. So the motion space is just the Hopf migration. So what does this mean? It means that your F and your H. So your F here is the generator of this cohomology group. So this is the data that you start with. You take your group SU2, it has a maximum torus U1, its quotient, so the base space for this is S2. Then the Langlands dual for SU2 is SO3. This you can find in any kind of thing.
So what is H? The class of H?
I'll get there in a moment because this is the thing that I think might be wrong about that paper. It's a normalization issue.
Okay.
But yeah, I mean, you tell me, what should it be?
7.
Okay, so from this, I would think that it should be 1, based on, yeah, we'll get there in a second. It's essentially how you normalize this H, right? So what's the killing form on SU2?
Some people use this Coxeter, they normalize it by the
Dual
Coxeter.
Coxeter number or something? Okay, well, there's some issue here, right? Because, yeah, anyway, the dual from here, and if I'm thinking of it as SO3, then the subgroup is, the maximum torus is probably SO2, which is just, obviously it's the same group, it's just a different variant. Then the space is SO3 on SO2, which is a constant test. And you get the exact same thing, F and H at. So now F is going to be, it's going to be 2. That's the answer. Is that SO3 is also the lens-based L1, 2. It's also S3 mod Z2. It's a bunch of other things. But this is precisely what you get out of T-duality, is that if this is a 2, then you get this is 2. So you get an interchange of F and H, as you would in normal T-duality. Okay, so the answer to the question at the start is Langlands duality a type of T-duality? And the answer is for E, F, G. For anything that's not type B or C, the answer is yes. And the H-box that you have to use in order to get this is precisely the Cartan freeform, which is a relatively natural freeform in the context of big groups. Okay. For those who are interested, this is a table of examples of groups and their duals. The one like SUN and SUN and SO2N is self-dual and things like that. Very
Yeah, I know, they are online.
The thing that I have here written down across that is SPN is dual to SO2N plus 1. So odd SO groups dual to SP2N, but that's the BC swapping BC, so that's why it's not this. Questions? Yeah.
So if we exclude this B and C, it basically means, I mean, modulo, if you say you work with simple examples, simple groups, then this would mean that these dual spaces are one covering, or like, okay, not necessarily cover of the other, but something like that.
For SUN, it's the case.
As a local homomorphic.
So an example is E8 is self-dual. So self-dual. So it's Langlands dual group is self-dual. And what that would correspond to in the T-duality sense is a kind of. For E8 you have E8 quotient by its maximum torus, which is a rank 8, I think. Yeah, I think it's 8-dimensional torus. So this is a principal T8 bundle over whatever this quotient space is.
Over its quotient.
Over its quotient. And then you're doing T-duality on this, so you're doing an 8-dimensional T-duality nonsense to get that it's dual to itself. Well, that's the
Right, so statement here is trivial. I mean, in this case. Or is it?
I wouldn't say that. Well, if I take SU2 with 1 unit of flux, then T-duality says it's self-dual. But I wouldn't call that a trivial statement, because I mean, at least, like topologically, yes, it's saying nothing happens topologically, but if I'm thinking this as the topological shadow of some actual geometric physicsy stuff, a whole bunch of stuff goes on even if the topology stays the same.
So you're saying maybe F and H have different, can be different. In this case, and maybe it's fault.
Yeah, here it is exactly the same. So F and H.
What for this E8 case?
E8 case. If you use the Cartan 3-form, then nothing, the topology doesn't change. I could take a different multiple of the Cartan 3-form. I could take some other H flux. Right? If I take E8 by its maximal torus and I take a different H flux, not the Cartan 3-form, then the dual space idea will be different. Then that's just normal T-duality, right? If I take a torus bundle with some H flux, I can do T-duality on it and get something new. It's just that it's not going to give me the Langlands dual.
Right, I know. I guess I wanted to ask was that if you take the Cartan 3 form here, and then you go it, then you get again the 3 form, and you get again the Cartan 3 form? Yes.
So here we have then E8 over, it's self-dual in a sense.
Right. But why isn't this then? Why is this non-trivial?
I mean, topologically, it's kind of trivial.
Yes.
But if I'm thinking of this as the topological shadow of a T-duality, where I take E8 as a 20 T8 torus bundle, I mean, the geometric data in this is probably going to be crazy.
So for example,
it's almost an accident that the topology is the same.
If you, for example, take this like cohomology map, it will not be identity, right? Or will it?
Yeah, maybe that's another statement. And in fact, I don't know. Maybe that's.
Do you mean the twisted cohomology or?
Yeah. So this, I mean, T-duality always gives you a map of twisted cohomologies. In this case, so in the very simplest case, if you're doing a circle bundle, then it's a degree shifted isomorphism, right? Because your cohomology over here is concentrated in odd degrees, and over here it's in even degrees, and so you have to have a degree shifting in the cohomology. In this case, you're doing, think of it like doing 8 T-dualities individually, so it's going to map you to the same, even to even or odd to odd. So maybe it's the identity, but it could be not true.
I think it shouldn't be identity.
It would surprise me greatly if it was. Right. Yeah.
You think it should or shouldn't?
No, shouldn't. I think.
But certainly, T-duality. I like to think that T-duality exists beyond this topological description. That this is just a description of some small part of it, right? That there's really a whole bunch of stuff going on, and yes, in this case, it turns out to be remarkably nice. But yeah, that doesn't mean that the rest of it is true.
It breaks down for F4 and G2.
No, nothing. Right, no, I did say that they were type. What breaks down? No, I think it works for this as well.
Yeah, because the final statement is for ADE groups.
Yeah.
The flux, the Cartan free form is defined. Compact simple groups and.
So okay, so on the plus side, yeah, what you're saying is certainly true. That like the way it's stated in the paper is for ADE groups. The easy thing about it is that there's only 2 things to check, right? You look at F, like there's only one F, right? It's F4. It has some maximal torus, so you can look at that and you can write down the Cartan 3-form and check. I mean, it should be self-dual, or AD. Yeah, it should be self-dual. And same thing with G2, but I may be placing less confidence on that statement than the rest of it.
Is E7 self-dual?
Well, what's the Langlands dual of E7?
No idea.
Because the answer is, actually, that's the same answer with what you just said there. What is the Langlands dual of F4? because that's what the answer is, right? This is saying that the okay, no, actually, that's not true. So for E7, whatever the Langlands dual of E7 is, that's what the T-dual of it is of E7 if you take the Cartan through.
Yeah, I was thinking that if
I know that E8 is self-dual, that's why I wrote it down. I don't know about E7 or anything else.
E7 is a 7-dimensional torus, so then we do an odd number of T-dualities, so
Yep.
then according to what you said, there should be a degree shift in the vector.
In the isomorphism of twisted cohomologies, yes.
So then it cannot be, even if it would be the same thing.
Exactly, yeah. This is why I was also not entirely sure about the E8 example, because it does make degree shifts, and we if we had to do that, yeah, and I mean, these are far more complicated than you would ever do in normal T-duality, right? If I wanted to write down geometric data and do Bushel procedure and stuff. I mean, E8 is how many dimensions? 256?
48.
248. Okay, divided by its dimension of its maximum torus, which is 8. That's going to be like 20 something, at least.
240.
240.
240. Sorry.
Divided. 32, maybe 31. Yeah, very good. But certainly.
No, no.
That's okay, so
Subtract dimensions, quotient subtracts dimensions.
okay, well,
Minus.
okay, that's much worse. I wasn't even happy doing 30.
Sorry, what was the dimension of E8?
240.
Yeah, the dimension of this mix, it's more than I'm comfortable dealing with. I think that's the best.
Okay, so enough powers, you can put it.
Yeah, exactly. Okay. And again, this is not a thing that you would actually think about doing. Like, E8 is not an example that will pop up in string theory, right? Your space-time is never E8. The dimensions are too large, right? Your space-time dimension is 10, 11, 26 at the most, right? You're certainly not going to take something that's 200 dimensional. So this is kind of more of an abstract statement about
Who knows?
but the lower dimensional ADE groups kind of work.
May I have a question?
Yes.
I know nothing about Langlands duality, but also did something about representations.
Yeah,
So does this story tell something about representations?
this is the reason why I decided to give this talk, because Andrea gave a talk 2 weeks ago, was it?
2 weeks ago.
Yeah, which has a lot of these words in it, and I didn't understand any of them, but I knew that yeah. So the answer is that this is a very different type of Langlands, like a very different description of Langlands dual things than how it normally appears. But there are kind of superficial similarities, and my question is, are those superficial similarities, like, is there anything deeper to that? Or is it they just are superficially similar? And that's kind of why I was giving this talk, because I was hoping that someone would look at this and say, yes, okay, maybe there is something deeper here, or actually, no, it's just kind of superficial.
I think there is. I mean, this should be the starting point for the Langlands duality. Now you have the duals, and you look at the principal bundles with connections from them. I don't know how there should be some form. I don't know, maybe because of the flux, there should be some duality, electromagnetic duality, S-duality. So I guess you build the S-duality on top of the T-duality as well. And you look at exactly this stack of principal G bundles with flat connection or the connection which is weird. And this should give you. I mean, the groups are so nice that they should correspond to one.
Right, yeah. That's part of what I was suspecting, was that it kind of, it fit too nicely for it to be, like, if it was a coincidence, it's a remarkable one.
Yes.
Like that. But certainly this is a much lower brow conversation, this stuff, than the usual description of Langlands duality, right? Because there it's heavy machinery, is the phrase I would use. This is easy stuff. Like it's differential geometry, it's differential forms and metrics and circle ones, right? Yeah.
So it also implies that the Langlands group, the liquid group and Langlands group have the same K theory, right?
twisted, right?
Twisted by this.
Equivariant twisted.
Yeah, equivariant twisted K-theory. Twisted precisely by the cross-country.
Yeah, twisted
that's-
equivariant.
Some
Twisted equivariant.
other meanings or not?
I would be surprised if it wasn't. Mathematicians tend to know a lot of things.
But then, since the twisted equivariant K-theory is the same as Bermuda group, these famous papers by Hawkins, and Talman. So what does it say about conformal field?
To answer your question,
Representation of
I expect
the
that it was probably done in the 1800s by some mathematicians where they realized that these twisted K-theories are the same.
Yeah, probably.
There's been a few different, so T-duality being reformulated in a few different mathematical contexts, and in each of these contexts, so I think it's called Laplace duality in some C-star context or something, but basically mathematicians discovered this, 30 years ago at least, or 50 years ago or something.
And there is some ADA classification of unitary conformal. ADA classification of some conformal field theories.
I think this has nothing to do with this, but I think that I think it's just that B and C, because of their structure of their Cartan matrices, because they're not symmetric, like these are the not symmetric ones, right? So if you're gonna have differences, like if you have some Cartan Deacon classification of something, then the objects in this classification that are going to be different kind of have to be the BC, right? And it has to be anything that is going to take the transpose of a Cartan matrix is going to swap B and C. Yeah, these Deacon diagram classifications pop up actually remarkably frequently. It's not just finite complex things, it will be others. Okay, just some people.
We'll be back at 4 o'clock, so I'm.
Yeah,
half an hour.